Good morning, guys. Today we are going to derive pressure equation. Children, this pressure equation is a very important concept in kinetic theory of gases, and it is given by P is equal to 1 by 3 rho C square, where rho is the density of gas and C is the RMS velocity, root mean square velocity. Now children, to get pressure, let us start from our concept. What is pressure? Ask this question to yourself and you are sure that pressure is force per unit area. So children, you want to get pressure, you should know the force. You should know the area. Area will be got by length into breadth. But to get force, what you'll do? Yes, we all know that. According to Newton's second law, force is equal to the rate of change of momentum. So in order to get force, you must have change in momentum of the molecules of gas, and the time interval between two successive collisions will help us further. So now you want pressure, you want force. To get force, you want change in momentum, and you know change in momentum will be equal to final momentum, that is after collision, minus initial momentum. So in order to get the change in momentum, we must have final momentum and initial momentum. So now you have understood the steps. If you remember them, I'll be able to solve the entire derivation for you, and even you will be able to solve it without seeing, I assure you. But remember that to get pressure, you should have force. To get force, you must have change in momentum. To get change in momentum, you must have final momentum minus initial momentum. Now, to understand, let's begin with simple. Let's have a gas. Let's have a container. So we'll have a three-dimensional container. In order to explain this to the examiner, okay, so this is a container. Now guys, let's put them the edges along the axis. So we have the Cartesian coordinate system. This will be the origin. Let this be x-axis, let this be y-axis, and let this be z-axis, and we will have an entire gas. Let m be the mass of gas, let small m be the gas of mass of each molecule of gas. Then we can have m is equal to n capital M, where n is the total number of gas molecules. It will be small m, so yeah, capital M will be n into small m, where n is the total number of gas molecules we have. Now children, the gas molecule, let's have one single gas molecule. Now this gas molecule is having random motion. So if you see its velocity, let it be here somewhere. Let its velocity be c1 bar. This is RMS velocity, which can be resolved into how many components? Maximum we can have 3 components as far as our syllabus is concerned. So we'll have 3 components, one along x-axis, let it be u bar, u1 bar, vector u1, and this will be v1, vector v1, and z component will be vector omega 1. So we can have the speed, RMS velocities, speed of gas molecules as C1, C2, Cn, where we will get the components resolution as C1 bar is equal to U1 bar plus V1 bar plus omega 1 bar. Now children, we can get the mod of it as square root of U1 square plus V1 square plus omega 1 square. So squaring both sides, we get C1 square is equal to U1 square plus V1 square plus omega 1 square. So similarly, we can have C2 square is equal to U2 square plus V2 square plus omega 2 square. In this way, if you have Cn square is equal to Un square plus Vn square plus omega n square. So this is the basic to get the pressure equation. As we all know the steps, remember, you know the steps, that still those are for getting pressure you must know the force, for getting force you must know the change in momentum, and to get change in momentum you must have initial momentum and final momentum. Now what about this gas molecule? Let us talk about this gas molecule. The same gas molecule having mass m, moving along the x-axis with U1 bar velocity and colliding with the wall. Colliding with this wall. Now when this molecule is moving, its initial momentum P1 bar will be equal to, definitely children, mass into, yes, U1 bar. So mass into velocity, this will give you the initial momentum. After it collides, it returns back. As it returns back, its velocity will be minus without changing its mass. So its final momentum will be equal to minus m U1 bar. Now as we have got both the momentum final as well as initial, we can have change in momentum as dp bar of gas molecule will be equal to P2 bar minus P1 bar. So this will give you minus m U1 bar, and this minus sign of the equation another magnitude, and then you will put it together as minus 2m U1 bar. So this is change in momentum of gas molecule. Now we all know who is colliding. The gas molecule is colliding with the wall, and according to law of conservation of momentum, the net change will be always equal to 0. To have that, the dp bar of wall must be equal to, if we want to have 0, so this will be minus 2, so this will be plus 2m U1 bar. So this will be the main component which will produce the force, which will further be giving the pressure. So this is what is needed, that is change in momentum. Now the most important question after change in momentum is to get the time interval. Let's understand the time interval between two successive collision, children. Time interval between two successive collisions. Yeah, we have two walls, one on each side here. Let's talk about these two walls. This is a very important concept. Suppose the gas molecule hits here, okay, and then goes and again hits here. Say this. So it goes and hits this molecule at any instant t is equal to 0 second. Comes back, it hits and comes back. So between two successive collision, again it has to hit the same wall, second collision. So this is first collision, this is second collision. So after first collision, it has to run twice. So it has to cover a distance of 2L with a velocity u bar. So its speed, velocity, speed is equal to speed, here magnitude wise velocity will be speed, speed is equal to distance upon time. Now we want to get the time interval between two successive collisions. We can have the time interval dt will be equal to total distance covered 2L upon its speed u1. So this is for first molecule what I am talking about. Now as we have got change in momentum, yes, and we have got dt, we can have a rate of change of momentum, yes, force F of first molecule. What is the force F1? Yes, you all know, according to Newton's second law, it will be dp1 upon dt. This will be further, as we know, it is plus 2 m u1 and divided by dt. Dt is 2L into u1. Yes. So in this way, we get force of the first particle as 2 m u1 square upon 2L. This 2 gets cancelled, so it will be m u1 square upon L. This is force of first molecule. In this way, you can get force of second molecule as along x-axis, of course, mu2 square upon L. And in this way, for nth molecule, you can have mun square upon L. So this is a very important equation. This is force of nth molecule along x-axis. So total force Fx will be equal to the addition of them. Let's add them together. This one, this one, this one. Can we have something common? Yes, we can have m by L common into the bracket u1 square plus u2 square plus we can have dot 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 for nth molecule un square. So this is force. We have got force. After change in momentum, we have got force, and after force, we can get pressure along x-axis. Pressure along x-axis is equal to force along x-axis per unit area of collision. So as you all know, this wall, yeah, if we have L as length of the wall, then the area will be, of course, L square. So we have Fx as m by L. The area comprises of L square and m by L, and multiply by this entire, it will be u1 square plus u2 square plus whole, that is un square, in this way. So this is what is px. This is px. So we have m by L, and rest all is the component along x-axis. So for y pressure, that is pressure along y-axis, just see m by L remains same, L square remains same, only this is going to change. Instead of x component, we will have y component, and y component already in resolution. We all know that the resolution of y component will be v. So therefore, instead of u children, we write v, we get pressure py. Let's go for it. So again, I'll mention that pressure px is equal to m mass of each molecule upon L into L. Square will be L cube into we have u1 square plus u2 square plus whole the molecule u square n. Hey guys, I hope you are getting the pressure along x-axis. So we all know L cube can be, yeah, L cube is the volume of entire container. So we have small m mass of each molecule again, and this is the entire volume into u1 square plus u2 square plus we have un square. So similarly, pressure along y, hey, pressure along y. So mass remains same, volume remains same, axis changes, the component changes. So it will be v1 square plus v2 square plus again vn square. Similarly, we can have pressure along z-axis as mass upon volume, and it will be omega 1 square, omega 2 square, and this will lead us to get omega square n. So this, we have got all the pressures. So the average pressure will be equal to px plus py plus pz, yeah, px plus py plus pz divided by 3. So in this way we can have the overall pressure as px plus py plus pz, because the pressure remains same. The pressure, you can go by different way as well, but this is one of the way. So we have p is equal to 1 by 3. So 1 by 3 we have got into the bracket. We will have addition of these three pressures. Can we have something common? Yes, we can have m upon capital V, common into the bracket, we can add them. See, now this addition u1 square plus u2 square plus dot 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 can be written as u1 square plus v1 square plus omega 1 square plus u2 square plus v2 square plus omega 2 square, and this u1 square plus v1 square plus omega 1 square plus, now we can have u2 square plus v2 square plus omega 2 square and dot 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 un square plus vn square plus omega n square. This will give me P pressure 1 by 3, again small m mass of each molecule, still volume, and then we can have C1 square plus C2 square plus dot 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 Cn square. Now here is the most important concept of root mean square velocity. Let's take another page for proper writing. We all know root mean square velocity, RMS velocity, to be CRMS. So the name itself suggests root mean. So we will have root mean, we will have mean. So suppose C1 plus C2 plus dot 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 Cn upon Cn. Let's square on both sides. We will have C square RMS. Cross multiply. If I cross multiply, I'll have n will be equal to C1 square. Yeah, it will be square because it is root mean square velocity. So C1 square plus C2 square plus dot 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 C square n. So see, for this we can, yeah, for this entire C1 square plus C2 square matter, this matter, what we can substitute is, we can substitute NC square RMS over here. For P is equal to 1 by 3 m by V. For this box we can, substitute capital N C square RMS or small n C square RMS. That doesn't make any difference. This n is number of gas molecules. So we'll have final answer P is equal to 1 by 3 mass of each molecule upon total volume into the bracket. We'll have N C square RMS. Now as you got P is equal to 1 by 3, see this, small m mass of each molecule and capital N total number of gas molecule will constitute the mass of gas upon volume C square RMS. Hey guys, I am happy because we are getting final answer. See, mass upon volume is density, children. So it will be rho and it will be C square RMS. So this is pressure equation. P is equal to 1 by 3 rho C square. Hey guys, this is my very first video holding the mobile cam in my one hand and giving this derivation. I know it should have been more perfect, but in the next lecture I am sure I'll rock. Students, please do post your comments for any improvisation, and soon by your blessings I'll get a camcorder. Yeah guys, for any doubts of physics, you can please put it in your comments, and sooner or later I'll get this equation. Thank you very much. Have a nice day.